Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's a thought experiment to gently bend your mind before we even begin. Think about a simple decision you made today. Maybe you chose to wear a blue shirt instead of a green one. Perhaps you decided to have toast for breakfast instead of cereal. Or maybe, just maybe, you're currently choosing to listen to these words instead of turning off your device and drifting straight to sleep. These are trivial choices, right? They don't seem to ripple through the fabric of the cosmos. But what if they do? What if at the very moment you made that decision, say choosing the blue shirt, an entirely separate reality sprang into existence? One where you woke up, considered the blue shirt, and then for no discernible reason reached for the green one instead. This isn't just philosophical musing or the plot of a science fiction movie. This is a concept that some of the most brilliant minds in physics have seriously proposed as a way to understand the fundamental nature of reality itself. It suggests that every single possibility, every single what if we can imagine, and countless others we can't, might not just be theoretical constructs, but actually real. Each choice, each interaction, each quantum event potentially splinters our reality into countless parallel branches, each one just as valid and concrete as the one you currently inhabit. It's a dizzying thought, a dizzying cascade of realities all unfolding simultaneously, an infinite echo of every conceivable what if. And the most astonishing part, the evidence for this radical idea stems from the deepest, strangest corners of quantum mechanics, the very laws that govern the microscopic world from which everything, including you, is ultimately built. It's a journey into the heart of reality, where the line between what is and what could have been blurs into an infinite tapestry. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's start with a question that seems almost absurdly simple. Why does anything happen the way it does? Why did that coin land on heads instead of tails? Why did that atom decay at that precise moment and not a microsecond later? In our everyday experience, we tend to believe in a fundamentally deterministic universe. If we knew all the forces acting on the coin, the exact flick of the thumb, the air resistance, the height, the spin, we assume we could predict with perfect certainty whether it would land heads or tails. This is the realm of classical physics, the physics of billiard balls and planets, where causes lead to predictable effects. Newton's laws of motion, for instance, tell us that if you know the initial conditions of a system, you can predict its future state precisely. It's a comforting thought. A universe operating like a perfectly calibrated clockwork mechanism. But here's where things get genuinely strange, and where our classical intuition begins to break down. When we zoom in, far past the scale of billiard balls and even past the scale of individual atoms, down into the quantum realm of electrons, photons, and quarks, that clockwork predictability vanishes. At this minuscule level, the universe doesn't behave like a perfectly predictable machine. It behaves more like a dice roll or perhaps a cosmic coin flip. This is the domain of quantum mechanics, a theory developed in the early 20th century to explain phenomena that classical physics simply couldn't account for, like why atoms don't collapse, or why light sometimes acts like a wave and sometimes like a particle. And it is in this quantum realm that the seeds of parallel universes are sown. At the heart of quantum mechanics lies the concept of a wave function. Now, don't let the name intimidate you. Conceptually, it's a way of describing the state of a quantum particle, like an electron before we observe it. Imagine an electron. Before we look at it, before we measure its position, it doesn't actually have a definite position in the way a billiard ball does. Instead, its position is described by this wave function, which represents a superposition of all possible positions the electron could be in. It's like the electron is simultaneously everywhere it could possibly be, spread out across space, a ghostly wave of probability. This isn't just a matter of our ignorance, as if the electron does have a definite position, but we just don't know it. No, quantum mechanics insists that the electron genuinely doesn't have a definite position until something interacts with it, until a measurement is made. And this is where the profound mystery and the idea of parallel universes truly begins to take shape. What happens when we do measure the electron's position? According to the standard interpretation of quantum mechanics, the act of measurement causes the wave function to collapse. All those myriad possibilities, all those potential positions the electron could have been in, suddenly vanish, and the electron snaps into a single definite position that we observe. It's as if a cosmic die is rolled and only one face comes up while all the other potential outcomes simply cease to exist. But here's the crucial, unsettling question. Why? Why does the act of observation or interaction cause this collapse? What is so special about measurement that it forces reality to choose a single path out of many? This is known as the measurement problem, and it has vexed physicists for nearly a century. To illustrate the absurdity of this problem, Austrian physicist Erwin Schrödinger devised his famous thought experiment, Schrödinger's cat. Imagine a cat sealed in a box with a vial of poison, a hammer, and a tiny piece of radioactive material. The radioactive material is set up so that there's a 50% chance over an hour that a single atom will decay. If it decays, it triggers a Geiger counter, which releases the hammer, which smashes the vial, which releases the poison, which kills the cat. If the atom doesn't decay, the cat lives. From the perspective of quantum mechanics, until we open the box and measure the state of the atom, that atom exists in a superposition of both decayed and undecayed states simultaneously. And if the atom is in a superposition, then the entire system linked to it must also be in a superposition. This means, according to the literal interpretation of the wave function, that the cat itself is simultaneously both alive and dead until we open the box. This is clearly nonsensical in our everyday experience. Cats are either alive or dead. They don't exist in some gruesome quantum limbo. The Schrödinger's cat paradox highlights the central difficulty of the measurement problem. If quantum rules apply to everything, and they seem to, then how do we get from a world of fuzzy, probabilistic superpositions to the concrete, definite reality we experience every moment? How does the collapse of the wave function actually happen? Who or what is doing the observing that forces reality to pick a single outcome? Is it a conscious observer, a measurement device, or is there something else entirely at play? Something that suggests the cat isn't really both alive and dead, but rather both possibilities are equally real, just in different places. That radical thought that every single quantum coin flip, every decay, every interaction doesn't force a single outcome, but rather causes reality itself to branch, is the foundational idea behind the many worlds interpretation of quantum mechanics. It's a universe where every what-if becomes a tangible reality, an infinite echo resounding through the cosmos. We've only just begun to scratch the surface of this mind-bending concept, exploring the quantum weirdness that gives rise to the very idea of parallel universes. We've seen how the seemingly simple act of observation challenges our understanding of reality, and how a cat can be both alive and dead. In our next chapter, we'll dive deeper into the many worlds interpretation itself, exploring what it truly means for reality to constantly split, and how this radical idea attempts to solve the perplexing measurement problem once and for all. Welcome back to Dreamy Science, where we journey into the heart of reality, one mind-bending concept at a time. Last time we left off peering into the infamous measurement problem in quantum mechanics, that baffling moment when a quantum particle existing in a ghostly superposition of all possible states suddenly chooses one definite reality the instant we observe it. We introduce Schrödinger's poor hypothetical cat trapped in a box, simultaneously alive and dead until its fate is witnessed. It's a paradox that has haunted physicists for nearly a century, suggesting that consciousness, or at least observation, plays a strangely active role in shaping reality. But what if the cat isn't both alive and dead in one reality? What if instead the universe itself simply branches, creating a new reality for each possible outcome? This, my friends, is the radical yet elegant proposition of the many worlds interpretation, MWI. Let's unpack this dizzying idea, shall we? Grab your cosmic compass, because we're about to explore a universe far grander and more intricate than you might ever have imagined. The core of MWI, developed by Hugh Everett III in 1957, is deceptively simple. The wave function never truly collapses. Remember that wave function. It's the mathematical description of all the potential states a quantum system can be in. In the standard Copenhagen interpretation of quantum mechanics, observation causes this wave function to collapse, forcing the system into a single definite state. But Everett said, no, that's not quite right. Instead, in the many worlds interpretation, every single time a quantum event occurs, whether it's an electron deciding where to land on a screen, a radioactive atom decaying, or even just a photon interacting with a molecule, the universe doesn't pick one path. It splits. It branches into separate non-communicating realities, each representing one of the possible outcomes of that quantum event. Think of it like this. Imagine you're at a fork in a road. In our everyday experience, you choose left or right, and the other path remains untravelled. But in the many worlds universe, when you reach that fork, the universe itself splits. One copy of you goes left, experiencing that reality. Another copy of you goes right, experiencing that reality. And both realities are equally real, equally valid, and equally populated by a version of you. Now extend this to the quantum realm. Take our friend, the electron. Before observation, it exists in a superposition, a cloud of probability, potentially here, there, or anywhere in between. When we set up a detector to see where it is, what happens according to MWI? The universe splits. In one new branch, the electron is detected here, and the observer, us, sees it here. In another branch, the electron is detected there, and a different version of the observer sees it there, and so on for every possible location. This is MWI's profound answer to the measurement problem. There is no collapse. The wave function doesn't disappear or reduce. It continues to evolve, describing all possible realities simultaneously. What we perceive as a collapse is merely our own branch of the universe experiencing one specific outcome, while other branches experience other outcomes. So what about Schrödinger's cat? How does MWI save our feline friend from its quantum limbo? In the MWI, when the quantum trigger, say the radioactive atom, decays, the universe splits. In one branch the atom decays, the poison is released, and the cat is dead. An observer in that branch opens the box and finds a dead cat. Simultaneously, in another, equally real branch, the atom doesn't decay. The cat lives, and an observer in that branch opens the box to find a live cat. The cat is never truly both alive and dead in the same universe. Instead, there is a universe with a live cat and a universe with a dead cat, and the act of observation simply separates the observer into corresponding branches, each experiencing a definite, singular reality. From the perspective of each observer, the outcome is clear and unambiguous. The superposition of the cat being both alive and dead is not a state within a single reality, but rather a description of the state of the entire multiverse, before it has branched into distinct realities. It's a truly mind-bending concept, isn't it? It means that every single quantum interaction, every dice roll of the cosmos, every probabilistic flick of a subatomic particle isn't just a decision made by the universe. It's a moment of cosmic fission, giving birth to new distinct realities. The sheer scale of this idea is almost incomprehensible. Imagine the number of quantum events happening right now in the atoms that make up your body, the air around you, the light hitting your screen, each one potentially a branching point. This continuous branching leads to an unfathomable number of parallel universes constantly being created. We're not talking about just a few alternative timelines. We're talking about an infinite, ever-expanding cosmic tree, where every conceivable what-if finds a home in its own unique branch. But if this is happening all the time, why don't we feel the universe splitting? Why do we perceive a single, continuous, coherent reality? This is where the concept of decoherence becomes critical. Imagine those branches of the universe. They don't just spring into existence, they quickly become decohered. Decoherence is essentially the process by which quantum systems lose their quantumness and start behaving like classical systems. It happens when a quantum system interacts with its environment. Even a single stray photon or air molecule is enough. These interactions cause the different branches of the wave function to become effectively isolated from each other. They stop interfering with each other, much like ripples in a pond that spread out and no longer affect each other once they've travelled far enough. So when the universe splits, say, over the fate of Schrödinger's cat, the observer also becomes entangled with that outcome. One version of you is now in a universe where the cat is dead and your brain state reflects dead cat. Another version of you is in a universe where the cat is alive and your brain state reflects live cat. These two versions of you and their respective realities are now decohered. They can no longer interact or even be aware of each other. From your perspective, each of your perspectives, reality is singular and definite. You simply exist in one of the branches, completely unaware of the countless others that have diverged. This means that the collapse of the wave function isn't a physical process destroying other possibilities. It's a subjective experience. From the internal perspective of an observer within a branch, the world appears classical and deterministic. We experience the world as having made a choice, but in the larger multi-universal picture, all choices were made, each in its own reality. This interpretation elegantly solves the measurement problem without introducing any mysterious consciousness causes collapse mechanism. The observer is no longer a special entity outside the laws of physics. They are simply another quantum system, subject to the same branching process. It's a purely deterministic theory, where the wave function always evolves according to the Schrödinger equation, without any unpredictable jumps or collapses. All the probabilities inherent in quantum mechanics are realized not as chances in one universe, but as certainties in different universes. The implications are staggering. Every decision you've ever made, every coin you've ever flipped, every path you've ever chosen, And every path you didn't choose has in some sense played out. There's a universe where you took that job and another where you didn't. A universe where you said yes and another where you said no. This isn't just about your personal choices, though. It's about every single quantum event, from the Big Bang to the present moment. It's easy to get lost in the sheer scale of it, to wonder if these other yous are truly you. From the perspective of MWI, you are a collection of yous across an infinite number of branches, each experiencing a unique, continuous path through the multiverse. When a split occurs, your consciousness, your very sense of self, also branches. There is no single you that experiences the branching, rather, new yous are created, each inheriting a portion of your past and diverging into a new future. This radical idea isn't just science fiction, it's a serious contender in the world of theoretical physics, favoured by many prominent scientists because of its mathematical elegance and its ability to resolve the measurement problem without introducing new, unproven mechanisms. It takes the quantum weirdness we discussed in Chapter 1 and superposition and probability and extends it to its logical, if mind-boggling, conclusion. All possibilities are realised. Of course, it is not without its critics. Some find the idea of an infinite number of universes too extravagant, too wasteful. Others grapple with the philosophical implications of identity and free will in a branching cosmos. But for now, we're just exploring the terrain, aren't we? We've delved into the heart of the many worlds interpretation, understanding how it proposes to solve the quantum measurement problem by doing away with wave function collapse altogether. Instead, it offers a continuously branching universe where every quantum possibility becomes a tangible reality in its own unique branch. It's a beautiful, terrifying, and profoundly awe-inspiring vision of reality. What do you think of this idea? Does it feel liberating to imagine every possibility playing out, or does it feel overwhelming? I'd love to hear your thoughts in the comments below. And if you're enjoying this journey into the profound mysteries of physics, please hit that like button and subscribe to Dreamy Science for more explorations into the cosmos. Next time, we'll continue our journey by exploring some of the philosophical dilemmas and practical challenges posed by the many worlds interpretation, and we'll even peek at some of the other fascinating, if less popular, interpretations that attempt to make sense of quantum reality. Because the story of parallel universes is far from over, and the rabbit hole, as always, goes much, much deeper. Welcome back, curious explorers, to Dreamy Science, where we unravel the universe's most mind-bending concepts, one patient step at a time. Last time we dove headfirst into the many worlds interpretation, or MWI, a truly radical solution to the quantum measurement problem. We learned that instead of a wave function collapsing, the universe itself branches with every quantum event, creating countless parallel realities. And we touched on decoherence, the elegant process that isolates these branches, ensuring we perceive a single coherent reality, even as an infinite cosmic tree constantly grows around us. Today we're going even deeper into the heart of MWI. Because while the idea of branching universes might sound like science fiction, its implications for how we understand reality, consciousness, and even our own identity are profoundly real, and frankly, a little dizzying. Let's begin by revisiting the observer. Remember how in earlier interpretations of quantum mechanics, there was this lingering question about the role of consciousness in causing the wave function to collapse? It was almost as if the universe needed a mind to make up its mind. But MWI sweeps that notion aside with a beautiful, purely physical elegance. In the many worlds interpretation, the observer isn't special, they aren't an external force dictating reality. Instead, the observer is an integral part of the quantum system itself, Think about it this way. When you perform a quantum experiment, say, observing an electron's spin, you're not standing outside the universe poking it with a stick. You, your measurement apparatus, the air around you, the light bouncing off the display, all of it is made of quantum particles. So when the electron's wave function interacts with your detector, and then that detector interacts with your brain, you become entangled with the electron's state. Under MWI, this entanglement isn't about you causing a collapse, it's about you being split along with the universe. In one branch, you observe the electron spinning up. In another, equally real branch, another version of you observes it spinning down. There's no magical collapse triggered by your consciousness. There's just the continuous deterministic evolution of the universal wave function, which includes you, me, and everything else within it. It's a deeply satisfying idea for many physicists because it removes any need for a mysterious non-physical element like consciousness to play a special role in fundamental physics. The universe simply unfolds, and we unfold with it. Now, this brings us to perhaps the most mind-bending aspect of MWI, the many yous. If every quantum event, and remember, these are happening billions of times per second, from the decay of an atom in the sun to the precise path of a photon hitting your retina, causes the universe to branch, then there are not just two versions of you, but an unfathomable number constantly multiplying. Let's pause and really let that sink in. Consider a simple everyday choice. You're at a coffee shop. Do you order a latte or a cappuccino? Classically, you make a choice and one outcome happens. But under MWI, even this seemingly trivial decision, driven by countless quantum interactions in your brain, your environment, and the world around you, could lead to a branching. In one universe, a version of you sips a latte. In another, a version of you savors a cappuccino, and it gets exponentially more complex. Did you choose the blue shirt or the red one this morning? In one universe, you're wearing blue, in another, red. Did you turn left or right on your commute? There are now branches where you did both. This isn't just about big life-altering decisions, it's about the constant microscopic quantum fluctuations that underpin every macroscopic event. Every single time a particle could go one way or another, every time an atom could decay or not decay, every time a photon could hit this detector or that one, the universe branches. And with each branch, a new version of you comes into existence, experiencing that specific outcome. So the question naturally arises, are these other yous truly you? And what does this mean for our sense of identity, for free will, for the very concept of me? From the perspective of MWI, yes, they are you. Or rather, they were you, up until the point of the quantum branching event. Each version of you in these parallel universes has the exact same memories, experiences, and personality as you did just before the split. They are not clones, they are continuations of your consciousness along a different path in the cosmic tree. You are the trunk, and each branch is a different trajectory of your existence. This view can feel unsettling. It challenges our deeply ingrained notion of a single linear self. If all possible outcomes of a quantum event are realized, does free will still exist? If every choice I could make is made by some version of me in some universe, does my specific choice here now truly matter? NWI doesn't negate free will entirely, but it certainly reframes it. Instead of seeing free will as choosing one future from the many, MWI suggests that our choices, driven by quantum processes in our brains, lead to the realization of all those futures across different branches. We don't choose not to make a choice. We simply experience the outcome of one specific branch while other versions of us experience the outcomes of others. It's a universe where every potentiality, every what if, is actualized somewhere. It's a universe of infinite possibilities all happening simultaneously, just to different versions of you. Now, if all outcomes happen, does that mean that the concept of probability becomes meaningless? This is a crucial question, and MWI offers an elegant, though subtle answer. When we talk about a 50-50 chance of a coin landing, heads or tails, or a particle decaying with a certain probability, what does that mean in a multiverse where both outcomes always occur? In MWI, probabilities are often understood in terms of the measure or weight of a branch. Imagine our cosmic tree of universes. Not all branches are created equal in this sense. Some branches, representing more probable outcomes, are often thought of as having a larger measure, or being thicker or more numerous than branches representing less probable outcomes. It's a bit like this. If you have a bag with 90 red marbles and 10 blue marbles, and you randomly pick one, you're much more likely to pick a red one. In MWI, if you were to branch into universes based on this pick, there would be many more branches where you picked a red marble than where you picked a blue one. So while both outcomes exist, the subjective experience of probability still holds because the vast majority of yous in the multiverse will have experienced the more probable outcome. It's not that the improbable outcome doesn't happen, it's just that there are fewer universes, fewer yous, in which it does. This interpretation of probability is one of the more debated aspects of MWI, but it allows the theory to remain consistent with all the statistical predictions of quantum mechanics that we observe in our single, perceived reality. The universe isn't just a collection of possibilities, it's a weighted tapestry of actualities. But this brings us to a common and very fair criticism of MWI. If these other worlds, these other branches, are truly separate and non-communicating due to decoherence, how can we ever prove they exist? How can we test MWI? It's true that direct experimental verification of parallel universes is incredibly challenging, if not impossible, with our current technology. We can't build a telescope powerful enough to peek into another branch, nor can we send a message to another version of ourselves. The very mechanism that makes MWI coherent, decoherence, also ensures their isolation. However, many proponents of MWI would argue that this isn't a flaw, it's a feature. MWI doesn't require any new physics or ad hoc assumptions beyond the standard Schrödinger equation, which describes how quantum systems evolve over time. It simply takes that equation seriously, without adding a mysterious collapse postulate. It's a minimalist interpretation in terms of fundamental laws, even if it's maximalist in terms of universes. Its elegance lies in its ability to solve the measurement problem deterministically, without relying on an external observer or a random, unexplained collapse. It's consistent with all observed quantum phenomena, and it offers a complete, albeit dizzying, picture of reality. Compare that to the Copenhagen interpretation which, while incredibly successful for predictions, essentially says, when you measure, the wave function collapses. Don't ask why. MWI, in contrast, explains why we perceive a single outcome. Because we're entangled with that outcome in our particular branch of the multiverse, and all other branches are, for all practical purposes, inaccessible. Where does this leave us? The many worlds interpretation presents a universe far grander, far more complex and far more awe-inspiring than we could have ever imagined. It suggests that every single quantum possibility isn't just a what if, but a what is, existing in its own unique, parallel reality. It means that the universe isn't just a story with one ending, but an infinite epic with every conceivable twist and turn playing out simultaneously. It's a profound shift in perspective, one that challenges our understanding of reality, causality, and even the very nature of our own existence. It asks us to consider that every moment is a branching point, and that countless versions of ourselves are living out every possible permutation of our lives. It's a vision of the cosmos that is both deeply deterministic and infinitely free, a scientific wonder that continues to fuel intense debate and endless fascination among physicists and philosophers alike. What do you think about the many worlds interpretation? Does the idea of infinite yous make your head spin, or does it fill you with a sense of cosmic wonder? I'm always curious to hear your thoughts in the comments below. If you've enjoyed this journey into the heart of parallel universes, I'd love it if you'd hit that like button, share this video with fellow curious minds, and of course subscribe to Dreamy Science for more explorations into the profound mysteries of our universe. Next time, we'll continue our slow explanation by grappling with some of the philosophical implications of MWI even further, and perhaps we'll even touch on some other theories of parallel universes. Until then, keep dreaming big and keep questioning everything. Alright, welcome back to Dreamy Science, our ongoing exploration into the truly wondrous and sometimes dizzying world of parallel universes. If you've been following along, you know we've just taken a deep dive into the many worlds interpretation, or MWI, a theory that suggests our universe isn't just one static reality, but an ever-branching cosmic tree. We talked about how every quantum event, from the decay of an atom to the spin of an electron, causes the universe to split, creating countless versions of you, each living out a slightly different path. Mind-bending, right? Now I'm sure many of you are thinking, okay, Dreamy Science, this sounds incredible, but if there are all these other universes, all these other me's, why don't I see them? Why do I only experience one reality? And that, my friends, is an excellent question. It brings us back to a concept we touched on briefly: decoherence. Imagine you're listening to a radio. You can tune into different stations, right? Each station is broadcasting its own unique signal, its own music, its own stories. But you only hear one at a time because your radio is tuned to a specific frequency. You don't hear all the stations playing at once, even though they're all out there, existing simultaneously in the air around you. Decoherence acts a bit like that. When a quantum system interacts with its environment, which, let's be honest, is always happening, it essentially tunes each resulting branch of the universe to a different frequency. These frequencies become so distinct, so separate, that they can no longer interact or interfere with each other. They become, for all intents and purposes, isolated realities. Our experience of collapse, that moment when a quantum particle seems to pick a definite state, isn't the universe choosing one outcome and discarding the others. It's simply us becoming part of a specific branch, a specific frequency, where that particular outcome is realized. The other outcomes are still out there, realized in their own branches, but they're now inaccessible to us. This process of decoherence happens incredibly fast, on timescales far too rapid for us to perceive directly. It ensures that once a split occurs, the resulting universes quickly become independent, unable to cross-communicate. This is why you don't see your other you who chose the blueberry muffin instead of the chocolate croissant. That other you is in a branch that has decohered, a separate reality that from your perspective is entirely unreachable. Now let's talk about something else that often throws people for a loop when they first encounter MWI. Probability. if every possible outcome of a quantum event actually happens in some universe, then what does it even mean to talk about the probability of an event? If you flip a coin and in one universe it lands heads and in another it lands tails, what's the 50-50 chance all about? This is where MWI offers a fascinating reinterpretation of probability. In the many worlds view, probabilities don't describe the likelihood of an event occurring, because all events do occur. Instead, probabilities describe the measure or weight of the different branches. Think of it like this. Imagine the universe as a giant pie. When a quantum event happens, that pie gets sliced up. The size of each slice corresponds to the probability of that particular outcome. So if you flip a fair coin, the universe splits into two branches, one where it's heads, one where it's tails. Both branches are equally thick or weighted. If you perform an experiment where an electron has a 90% chance of spinning up and a 10% chance of spinning down, then the universe splits such that the spin-up branch is 9 times thicker or more numerous than the spin-down branch. What this means for us, the observers, is that we are far more likely to find ourselves in the spin-up branch. It's not that the spin-down branch doesn't exist, it absolutely does, but the vast majority of yous will experience the spin-up outcome. The statistical predictions of quantum mechanics, which we observe in experiments every single day, are perfectly preserved within MWI. It's just that the underlying reality is far richer and more complex than we might initially imagine. This approach to probability is one of the more elegant aspects of MWI, as it doesn't require any new, ad hoc rules to explain why we perceive certain outcomes more often than others. It simply takes the mathematics of quantum mechanics, particularly the Schrödinger equation, which describes how quantum systems evolve, completely literally. The wave function, which mathematically describes all possible states of a system, is seen as a description of an objectively existing branching reality. Of course, no scientific theory is without its challenges and criticisms, and MWI is no exception. The most frequent and significant critique levelled against MWI is its testability. How do we experimentally verify the existence of these other universes if, by their very nature, they are utterly inaccessible to us due to decoherence? This is a profound philosophical and practical hurdle. Unlike other theories that predict observable phenomena, MWI's core assertion, the existence of countless parallel worlds, seems to defy direct empirical proof. Critics sometimes invoke Occam's razor, the principle that states, among competing hypotheses, the one with the fewest assumptions should be selected. They argue that positing an infinite number of universes for every quantum event is an unnecessary extravagance or a profligate use of reality. Why create an entire new universe just because an electron took a different path? However, proponents of MWI counter that while it might seem extravagant in terms of the number of realities, it's incredibly parsimonious in terms of its underlying physical laws. MWI doesn't add any new laws of physics. It simply removes the measurement problem by taking the existing well-established laws of quantum mechanics at face value without needing to invent a collapse mechanism. From this perspective, it's actually the simplest explanation, requiring the fewest ad hoc assumptions to make quantum theory consistent. Another point of discussion often revolves around the preferred basis problem. While the idea of splitting is elegant precisely what constitutes a branching event, or the fundamental basis upon which the universe divides is still a subject of intense debate among physicists. When exactly does the system become entangled enough with its environment to create distinct, non-interfering branches? These are complex technical questions that physicists continue to explore. Despite these challenges, the many worlds interpretation remains incredibly compelling to many physicists. Its elegance, its determinism at the level of the universal wave function, and its complete resolution of the measurement problem without introducing any mysterious observer effect make it a powerful contender in the quest to understand quantum reality. It offers a picture of the universe that is, in a profound sense, fully consistent with the mathematics we use to describe it. But let's return to the philosophical implications, because this is where MWI truly forces us to rethink everything we thought we knew about ourselves and our place in the cosmos. We talked about many U's in the last chapter, but let's dig a little deeper. If every quantum fluctuation, every decision you make, which at its root involves quantum events in your brain, every roll of the dice, every cosmic coin flip creates new branches, what does that mean for your personal identity? The you reading this right now is just one thread in an unimaginably vast tapestry of selves. There's a you who decided to skip this video, another you who's watching it for the 10th time, a you who pursued a completely different career, and a you who made vastly different life choices. Each of these yous is equally real, equally a continuation of the same initial you that existed before the branching event. This isn't about alternate realities in some abstract, disconnected sense. These are your continuations. This challenges our very notion of a singular linear self. It suggests that our consciousness isn't confined to one path, but rather diversifies and branches with the universe itself. And what about free will? If every possible outcome of a decision is realized in some universe, does that diminish the significance of our choices? If there's a you who makes the right choice and a you who makes the wrong one, and both are equally real, does that mean our decisions are merely predetermined branches on the cosmic tree? This is a deeply philosophical question, and MWI doesn't provide a simple answer. Some argue that free will is redefined. It's not about choosing one future, but about being the agent that initiates the branching into multiple futures, each representing a choice. Others find it unsettling, suggesting that if all possibilities are realized, the unique responsibility and agency often associated with free will might be diluted. What MWI does, unequivocally, is expand our understanding of what possible truly means. It takes the abstract probabilities of quantum mechanics and reifies them into concrete realities. Every path not taken, every choice not made, every random quantum fluctuation that could have gone differently, they all exist somewhere, with some version of you experiencing them. It's a dizzying thought, isn't it? The universe isn't just vast in space and time, it's also unfathomably vast in its very reality, constantly splitting, weaving, and expanding into an ever more complex web of possibilities. As we wrap up this chapter, I want to emphasize that MWI is just one interpretation among several, each trying to make sense of the profound mysteries of quantum mechanics, but it's arguably the most radical, the most audacious, and certainly one of the most intellectually stimulating. It forces us to confront the true strangeness of reality and to question assumptions we've held about existence, identity, and consciousness for centuries. What are your thoughts on MWI? Does the idea of many yous thrill you or unsettle you? Do you find its elegance compelling or its lack of testability a deal breaker? Let me know in the comments below. I'm always curious to hear your perspectives on these mind-bending topics. If you're enjoying this journey into the heart of reality, please hit that like button and consider subscribing to Dreamy Science. In our next chapter, we'll shift gears slightly and explore some other fascinating theories about parallel universes, moving beyond the quantum realm and into even more speculative but equally captivating ideas. You won't want to miss it, Until then, keep dreaming, keep questioning, and keep exploring the infinite possibilities of our universe. Or should I say universes? Alright, so we've journeyed through the mind-bending landscape of quantum mechanics, seen the perplexing paradox of Schrödinger's cat, and finally arrived at the elegant, albeit radical, solution offered by the many worlds interpretation. We've explored how it resolves the measurement problem by simply saying the wave function never collapses, how decoherence creates our seemingly singular reality, and how probability gets a fascinating reinterpretation. We even touched upon the dizzying idea of many yous, constantly branching off into untold futures. It's a truly beautiful framework, isn't it? It takes the fundamental equations of quantum mechanics, equations that have been incredibly successful in predicting experimental outcomes, and says, let's just trust them completely without adding any mysterious collapse mechanism. It's parsimonious in its laws, even if it's extravagant in its universes. But as with any truly revolutionary scientific idea, the many worlds interpretation isn't without its challenges, its critics, and its profound philosophical questions that stretch our understanding of reality and self. And that, my curious friends, is precisely what we're going to dive into today. We're going to tackle the major hurdles and ponder the deepest implications of a truly branching multiverse. First up, let's talk about the elephant in the quantum room: testability. One of the cornerstones of modern science is the ability to test a hypothesis, to design experiments that could either confirm or refute a theory. This is the principle of falsifiability, championed by philosophers like Karl Popper. If a theory cannot in principle be disproven by any conceivable observation, then some argue it falls outside the realm of empirical science. And here, MWI faces one of its toughest battles. Remember how decoherence works. It's the process by which our newly formed branches rapidly become isolated from each other. The interaction with the environment essentially seals off these parallel realities, preventing any information from passing between them. From our perspective, within our branch, the other universes are fundamentally inaccessible. We can't build a telescope powerful enough or a quantum device clever enough to peek into a neighboring branch and say, aha, there's the other me who chose coffee instead of tea this morning. This inaccessibility is often cited as the primary weakness of MWI. If we can never directly observe these other universes, how can we ever prove they exist? How can we differentiate MWI from, say, the Copenhagen interpretation, which simply says the wave function does collapse, even if we don't fully understand why? It's a valid concern and one that physicists grapple with constantly. However, proponents of MWI would argue that while direct observation might be impossible, there could be indirect evidence. Perhaps future quantum computing technologies, which rely on maintaining quantum coherence for extended periods, might reveal subtle effects or behaviors that are better explained by a non-collapsing, branching universe. Some theoretical physicists are exploring whether MWI makes unique predictions in certain extreme quantum scenarios that differ from other interpretations, though these are incredibly complex and at the very edge of our current understanding and experimental capabilities. For now, much of the argument for MWI rests on its elegance and its ability to solve the measurement problem without introducing any new, ad hoc physics. It's about taking the existing experimentally verified equations of quantum mechanics at face value without adding extra postulates. It's a philosophical argument as much as a scientific one at this stage, but the search for indirect experimental evidence continues. This brings us neatly to the next challenge, often framed as debate about Occam's razor. You've probably heard of Occam's razor, right? It's the principle that when faced with competing hypotheses that explain the same phenomenon, the one with the fewest assumptions is usually the best. Or, put simply, the simplest explanation is often the correct one. Critics of MWI wield Occam's razor like a mighty sword, arguing that positing an infinite number of universes for every single quantum event is an astronomically extravagant assumption. Imagine the sheer scale. Every electron flip, every photon interaction, every atomic decay, each one creating new branches, new universes. The number quickly becomes incomprehensibly vast. Surely, they argue, it's simpler to assume a single universe where the wave function just collapses. But here's where the MWI proponents push back with their own interpretation of Occam's razor. They argue that MWI is actually more parsimonious in terms of fundamental laws. Think about it. The Schrödinger equation, which governs how quantum states evolve over time, is a perfectly deterministic linear equation. It describes how a quantum system, including its observer, evolves into a superposition of all possible outcomes. The Copenhagen interpretation, on the other hand, adds an extra rule: the collapse of the wave function upon measurement. This collapse is non-deterministic, non-linear, and isn't derived from any fundamental principle within quantum mechanics itself. It's an ad hoc addition to make the theory fit our classical experience of a single reality. So the MWI argument goes, is it simpler to assume a single fundamental law, the Schrödinger equation, that applies universally and leads to an infinite number of realities, or to assume two fundamental laws, the Schrödinger equation plus a mysterious ill-defined collapse mechanism that only kicks in upon measurement? From this perspective, MWI is the simpler theory because it requires fewer axioms or fundamental assumptions about how the universe works. It simply takes quantum mechanics seriously all the way down. It's a fascinating debate, isn't it? It highlights how simplicity can be interpreted in different ways. Simplicity in the number of universes versus simplicity in the number of fundamental laws. I'd love to hear your thoughts on this in the comments below. Which side of Occam's razor do you find more compelling? Now, let's step away from the purely scientific and venture into the truly profound, the philosophical implications of the many worlds interpretation. This is where MWI truly challenges our everyday intuitions and forces us to reconsider our place in the cosmos. We've touched upon the idea of many yous. If every quantum event leads to a branching of the universe, and we are part of that quantum system, then every decision we make, every interaction we have, every random quantum fluctuation within our brains or environment creates new versions of ourselves experiencing different outcomes. This raises a dizzying question. What does it mean for personal identity? If there's a version of me in one branch who chose the blue shirt, and another version who chose the red, are they both me? If I make a morally ambiguous choice in one branch and a virtuous one in another, am I responsible for both? From our subjective perspective, we only ever experience one continuous thread of consciousness, one singular path through the branching multiverse. We don't feel ourselves splitting. We don't perceive the other us. The MWI doesn't necessarily say that you split. Rather, it implies that the universe splits, and you, as an integral part of that universe, find yourself on one of the newly formed branches. The you on the other branch is just as much you as the you here, having diverged at a specific point. It's like a river splitting into two streams. Both streams originated from the same river, but now they flow independently, Each you is a continuation of the same initial you, but experiencing a different path. It's a truly mind-bending concept that challenges the very notion of a singular, unchanging self. And what about our free will? This is perhaps one of the most unsettling implications for many people. If every possible outcome of a quantum event, and by extension, every possible choice you could make if we consider choices to be influenced by underlying quantum processes, is actualized in some parallel universe, does our choice truly matter? If there's a universe where I don't write this chapter, and another where I do, what does my decision to write it here signify? This is a deep philosophical rabbit hole. Some argue that MWI implies a kind of quantum fatalism, that all possible futures are preordained to exist, regardless of our perceived choices. However, another perspective argues that free will is still profoundly meaningful within your own branch. You're still making conscious decisions, and those decisions determine which branch will you experience. The existence of other branches where you made different choices doesn't negate the reality of the choice you made here. You still experience the act of choosing, the deliberation, and the consequences within your own experienced reality. Furthermore, remember our discussion about probability. Even if all outcomes exist, some branches have more measure or weight than others. Your choices, your intentions, your actions might influence the thickness or prevalence of certain types of branches. So while every possibility might be actualized, your actions still guide which realities become more real or common from a statistical standpoint. It's a subtle but crucial distinction. Finally, let's touch briefly on a more technical but still important challenge for MWI theorists, the preferred basis problem. This is a debate primarily among physicists working on the finer details of MWI. The question isn't if the universe branches, but rather when and how it decides which specific states are distinct enough to form separate decohered branches. Imagine a particle that can be in two energy states or two spin states. It's clear that these are distinct possibilities. But what about more subtle differences? How does the universe choose the specific basis, the set of fundamental properties in which it splits? It's a complex mathematical and theoretical challenge, but it doesn't undermine the core idea of MWI. Instead, it's about refining the details of how decoherence precisely leads to the emergence of our classical reality from the quantum superposition. It's an active area of research, with different theoretical approaches attempting to provide the most coherent and consistent answer. So there you have it, the major challenges and philosophical implications of the many worlds interpretation. It's a theory that is elegant in its scientific simplicity, yet breathtakingly complex in its cosmic implications. It solves one of quantum mechanics' deepest mysteries, the measurement problem, by presenting us with a universe far vaster and stranger than we could have ever imagined. Whether you find MWI compelling or deeply unsettling, it undeniably forces us to confront fundamental questions about reality, identity, and the very fabric of existence. It's a testament to the power of human curiosity and our relentless drive to understand the universe, even when that understanding pushes the boundaries of our intuition. As we continue our journey, remember that these are not settled debates. Physics is a living, breathing field constantly evolving. The many worlds interpretation is one of the leading contenders in the ongoing quest to make sense of quantum reality, alongside other fascinating interpretations we might explore in future episodes. If you've enjoyed this deep dive into the challenges of MWI, don't forget to hit that like button, subscribe to Dreamy Science for more mind-bending explorations, and drop a comment below with your thoughts on testability, Occam's razor, or what you means in a multiverse. Your insights truly enrich this shared journey of discovery. Next time we'll move beyond MWI and take a peek at some other fascinating interpretations of quantum mechanics, and perhaps even touch upon the idea of parallel universes arising from other cosmological theories. The multiverse, it turns out, is a concept with many different flavors, and each one offers a unique window into the strangeness of our universe. I can't wait to explore them with you. All right, fellow cosmic explorers, welcome back to Dreamy Science. If you've been with us on this mind-bending journey, you know we've spent the last few chapters really diving deep into the many worlds interpretation, or MWI. We've unpacked its elegant solution to the quantum measurement problem, the dizzying concept of many yous, and how decoherence keeps our perceived reality singular. But, as we acknowledged last time, MWI isn't without its profound challenges and unanswered questions. It's a truly beautiful theory, a testament to human ingenuity in trying to make sense of the universe, but it pushes the boundaries of what we can directly observe and even what we intuitively understand about ourselves. Today we're going to lean into those challenges a bit more, giving them the slow, thoughtful consideration they deserve. Because understanding the criticisms and open problems of a theory is just as crucial as understanding its strengths. It's how science progresses, after all. One of the biggest hurdles, a towering peak in the quantum landscape, is what we call the testability. Remember, MWI proposes that every quantum event, every measurement, every interaction causes the universe to branch into distinct non-communicating realities. In one branch, Schrödinger's cat lives, in another, it's gone. In one branch, you picked coffee, in another, you chose tea. But here's the kicker. These branches, once formed and decohered, are fundamentally inaccessible to one another. So how do you test a theory whose core postulate involves realities you can never directly observe? It's like trying to prove the existence of an identical twin you never knew you had, who lives in a house you can never visit, and who experiences a life you can never share. The very mechanism that makes MWI elegant, the universal validity of the wave function and the natural branching via decoherence, also makes it incredibly difficult to verify empirically. We can't build a multiverse detector to scan for other Earths where dinosaurs never went extinct, or where you became an astronaut instead of a podcast listener. At least not yet, and perhaps not ever, according to the theory itself. This isn't to say MWI makes no testable predictions. It does predict all the standard results of quantum mechanics that we observe in our single, perceived universe. But that's also the rub. So do other interpretations. The challenge for MWI is to offer a unique prediction, something that only MWI would explain, and that we could observe in our reality. Some physicists are exploring highly speculative avenues, wondering if there could be incredibly subtle, residual quantum correlations or interference effects that might hint at the presence of other branches, perhaps at scales far beyond our current experimental capabilities. But for now, these remain theoretical whispers in the vast silence between worlds. It's a fascinating area of ongoing research, and I'm always curious to see what new ideas emerge from that frontier. Now, let's talk about Occam's razor. This is the principle that given multiple explanations for an observed phenomenon, the simplest one is usually the best. Critics of MWI often wield Occam's razor like a mighty sword, arguing that postulating an infinite number of universes for every single quantum event is an extravagant, indeed, a wildly unparsimonious addition to our understanding of reality. Why create countless copies of everything just to avoid a collapse? It seems like a massive ontological overhead, doesn't it? But MWI proponents have a powerful counter-argument, and it's one that I personally find incredibly compelling. They argue that MWI is actually more parsimonious at a fundamental level. Think about it. Standard quantum mechanics, with its wave function and superposition, works beautifully right up until the point of measurement. Then it requires an additional postulate, the wave function's collapse, to explain why we only see one outcome. This collapse is an arbitrary, ill-defined process. When does it happen? What constitutes a measurement? Who or what is an observer? These questions have plagued quantum mechanics for decades. MWI, on the other hand, says, no collapse necessary. The wave function always evolves deterministically according to the Schrödinger equation, without any special, non-linear, unexplained process. The branching isn't an added postulate. It's the natural, inevitable consequence of the universal applicability of the Schrödinger equation to everything, including observers and measuring devices. The many worlds are not something extra that MWI adds. They're simply what reality looks like if quantum mechanics is truly complete and universally true, and if the wave function never collapses. From this perspective, MWI removes an ad hoc and problematic postulate, collapse, and replaces it with the universe that simply unfolds according to its own consistent deterministic rules. The infinite universes are a consequence of this simpler, more consistent set of fundamental laws, not an arbitrary addition. It's like saying that the vast number of leaves on a tree isn't unparsimonious, if the tree's growth rules are simple and elegant. The complexity arises from the simple rules operating over time. It's a powerful reframe, isn't it? It invites us to consider what simplicity truly means in physics. Simplicity of laws or simplicity of observed phenomena. Then there's the preferred basis problem. This is a more technical, but no less important challenge within MWI. If the universe is constantly branching, how does it decide which specific states constitute those branches? For example, when an electron spin is measured, it branches into spin-up and spin-down universes. But why those specific states? Why not a superposition of spin-up and spin-down states that are slightly different? Or some other more complex combination? How do the axes of the branching get chosen? The answer, as often happens in quantum mechanics, lies in decoherence. The environment plays a crucial role here. When a quantum system interacts with its environment, even a few stray air molecules or photons, the system quickly becomes entangled with that environment. This entanglement effectively selects a preferred basis, a set of states that are robust and stable against environmental interactions. These are the states that become the distinct, classical-like branches we perceive. So the preferred basis isn't arbitrarily chosen. It's dictated by the specific interactions between the quantum system, the measuring device, and the vast, messy quantum environment. While this offers a strong theoretical framework, precisely calculating and demonstrating this selection process for every scenario remains a complex area of research and refinement within MWI. It's about understanding the exact dynamics of how these distinct branches emerge from the underlying quantum soup. But perhaps the most profound, and for many the most unsettling challenges of MWI lie in its philosophical implications. We've touched on the idea of many yous before, and it's a concept that truly forces us to reconsider the very nature of personal identity. If every quantum event leads to a branching of your existence, then there are countless versions of you, each experiencing a different outcome for every choice, every random fluctuation. Which one is you? Is there a continuous self that persists across these branches, or do you simply cease to be, only for a new you to emerge in each branch, experiencing a distinct reality? This question strikes at the heart of our sense of self. We tend to think of ourselves as a singular, continuous stream of consciousness, but MWI suggests that this perception might be an illusion, a localized experience within one specific branch. The you reading this now is just one of an unfathomable number of yous who made slightly different choices or experienced different quantum outcomes in the past. It's a dizzying thought, truly. Does it diminish the uniqueness of your experiences? Does it make your choices less significant if every possible choice is actualized by some version of you? This leads us directly to the question of free will and responsibility. If all possible futures are realized in some branch, does our perceived ability to choose truly matter? In MWI, the evolution of the universal wave function is entirely deterministic, the branching is a natural, inevitable process. So while you in this branch might feel like you're making a choice, the you in another branch might be making the opposite choice, and both are equally real. Does this reduce our agency? Does it imply that our choices are merely the unfolding of a predetermined quantum script, played out across an infinite stage? And what about moral responsibility? If there's a version of you who performs a heroic act and another who commits a grave error, how do we assign responsibility? Does the good you cancel out the bad you in some cosmic ledger? These are not questions that physics can answer directly, but they are profound ethical and existential dilemmas that MWI squarely places before us. It challenges our fundamental assumptions about self, choice, and consequence. These are the deep waters of the many worlds interpretation, dear listeners. It's a theory that is elegant, consistent, and solves some of the most baffling problems in quantum mechanics, but it does so at a potentially staggering cost to our conventional understanding of reality, individuality, and free will. It's a testament to the sheer audacity of scientific thought that such an idea could even be conceived and seriously considered. But here's the thing, MWI is just one interpretation, albeit a powerful and widely discussed one. The quantum realm is so bizarre, so counterintuitive, that physicists have proposed many other ways to make sense of it, some of which also hint at different kinds of parallel universes or multiverses. So, as we bring this chapter to a close, I want to invite you to ponder these profound questions. What do you think about the testability of MWI? Does Occam's razor cut against it, or does it bolster its elegance? And how do you feel about the idea of many yous and its implications for your own identity and free will? Drop a comment below. I'd truly love to read your thoughts and engage with your perspectives. In our next chapter, we're going to step away from the many worlds interpretation for a bit and begin exploring other fascinating theories that suggest the existence of parallel universes. We'll look at ideas that arise from different corners of physics, from cosmology to string theory, each offering its own unique vision of a grander, multifaceted reality. It's going to be another journey into the truly unknown, and I can't wait to share it with you. If you've enjoyed this exploration, please hit that like button, subscribe to Dreamy Science for more journeys into the heart of reality, and share this episode with anyone you think might enjoy having their mind bent just a little bit. Until next time, keep looking up, keep asking questions, and keep dreaming big. This is Dreamy Science, signing off. Welcome back, cosmic explorers, to Dreamy Science, where we unravel the universe's most mind-bending concepts, one patient step at a time. Last time we dove headfirst into the quantum rabbit hole, emerging with the many worlds interpretation, a truly revolutionary idea suggesting that every quantum event splits our reality into countless parallel universes, each representing a different outcome. It's a dizzying thought, isn't it? The idea that there are many yous living out every possible choice, every quantum fluctuation, across an ever-branching cosmic tree. If that sent a shiver down your spine or made you question the very fabric of your personal identity, you're not alone. It's a profound re-evaluation of everything we thought we knew, and it challenges us to redefine concepts like probability, free will, and even what it means to be real. But here's the fascinating part. The many worlds interpretation, while radical, is just one way physicists conceive of parallel universes. It's rooted firmly in the strange counterintuitive world of quantum mechanics. Today we're going to broaden our horizons even further. We're going to explore parallel universes not just as a quantum phenomenon, but as a consequence of the vastness of space itself, and even as the natural outcome of how our cosmos began. Ready to expand your mind even more, settle in, maybe grab a warm beverage, and let's embark on this next leg of our journey. And if you're enjoying our slow, deliberate pace through these scientific wonders, do me a favor and hit that like button. It truly helps us reach more curious minds like yours. We've talked about how M2I posits an infinite number of universes branching off from quantum events. But what if parallel universes don't require quantum mechanics at all? What if they're simply a consequence of an infinitely large universe? Imagine for a moment that our universe isn't just big, it's infinite, truly endlessly, boundlessly infinite. This is the first type of cosmological multiverse we'll explore, often called the Level Y multiverse by cosmologist Max Tegmark. Now think about the stuff in our universe. Particles, atoms, stars, galaxies, and yes, even you and me. All of this is made up of a finite number of fundamental particles arranged in a finite number of possible configurations. It's like having a giant cosmic Lego set. You have a finite number of brick types, and though you can build an astonishing array of structures, if you have an infinite number of bricks and an infinite amount of space to build in, eventually you must repeat patterns. Consider a deck of cards. There are 52 cards and a finite number of ways to shuffle them. If you shuffle that deck an infinite number of times, eventually you're going to get the same sequence of cards again and again. The universe operates on a similar principle, but on an unimaginably grand scale. If our observable universe, that bubble of space from which light has had time to reach us, is just one tiny patch within an infinitely larger cosmos, then everything within it is destined to repeat. Somewhere, unfathomably far away, there's another patch of space identical to ours, and in that patch there's another Earth, another you, reading this very explanation, perhaps with a slightly different brand of warm beverage. This isn't a quantum split. This isn't a branching reality. This is simply the mathematical inevitability of infinite possibilities within a finite set of building blocks. Think of it this way. If you keep drawing numbers randomly, eventually you'll draw the same sequence again. If the universe is infinite, and the number of possible arrangements of matter within a given volume, like our observable universe, is finite, then statistical mechanics dictates that every possible arrangement must eventually occur, and recur infinitely many times. It's a mind-bending concept because it places an identical copy of you, down to every memory and every freckle, somewhere out there, perhaps trillions of light years away. And not just one copy, but an infinite number of copies living out your exact life, and lives that differ by just one electron's position, or one slightly different choice you made yesterday. The beauty of the level 1 multiverse is its simplicity. It doesn't require new physics or radical interpretations of quantum mechanics. It simply extrapolates from existing cosmological models that suggest our universe is flat and potentially infinite. The challenge, of course, is that these other U's are so far away that we can never hope to reach them or even observe them. They exist beyond our cosmic horizon, forever out of reach, yet conceptually, they're as real as the particles in your hand. So while the many worlds interpretation gave us many U's, branching through time, the level bay, multiverse gives us many U's existing through space, scattered across an infinite cosmic tapestry. Are you starting to feel a little less unique yet? Don't worry, there's more to come. Drop a comment below if you've ever considered the implications of an infinite universe. I'm always curious about your thoughts. Now, let's take another leap beyond the boundaries of our single infinite universe, into a realm where entire universes bubble into existence, each with its own unique set of physical laws. This brings us to the level 2 multiverse, often called the inflationary multiverse, or bubble universes. To understand this, we need a quick refresher on what's cosmic inflation. This is a leading theory that describes an extremely rapid, exponential expansion of the universe immediately after the Big Bang. Think of it like blowing up a balloon incredibly fast in the first tiny fraction of a second. This inflationary period smoothed out the universe, made it flat, and explains why the cosmic microwave background radiation is so uniform. It's a hugely successful theory that explains many observed features of our cosmos. But here's where it gets really interesting. The theory of eternal inflation suggests that this inflationary process, once it starts, might never truly stop everywhere. Instead, inflation might continue indefinitely in most regions of the cosmos, but in certain pockets it slows down and stops, forming distinct bubble universes. Imagine a vast, continuously boiling pot of water. The boiling represents the eternal inflation. Now, within this boiling water, bubbles of steam occasionally form, expand, and detach. Each of these bubbles, in this analogy, is a new universe. Our universe, with its galaxies and stars, is just one such bubble that stopped inflating and began its standard Big Bang expansion. The crucial difference between these bubble universes and the repeating patches of the level 1 multiverse is that these universes are truly separate. They are born from a larger, eternally inflating multiverse or meta-universe, and they can have radically different properties. What kind of different properties, you ask? Well, imagine a universe where the fundamental constants of physics are different. Maybe the speed of light is faster or slower. Maybe the gravitational constant is stronger or weaker. Perhaps the number of dimensions is different, or the types of particles that exist. Each bubble universe could be a unique cosmic experiment, governed by its own particular rulebook. This idea offers a compelling solution to one of the biggest mysteries in physics, the fine-tuning problem. Why are the physical constants in our universe so perfectly tuned to allow for the formation of stars, planets, and ultimately life? If gravity were slightly stronger, stars would burn out too quickly. If the strong nuclear force were slightly weaker, atoms wouldn't hold together. It's as if someone dialed all the cosmic knobs to just the right settings for us to exist. In a level 2 multiverse, this fine-tuning isn't a miraculous coincidence. It's a statistical inevitability. If there are an infinite number of bubble universes, each with randomly varying physical constants, then it's no surprise that we find ourselves in one of the rare universes where those constants do allow for life. We simply couldn't exist in any of the others. This is an application of the anthropic principle. We observe the universe to be the way it is because if it were different, we wouldn't be here to observe it. So, while MWI gave us all possible outcomes of quantum events and Level 1 gave us infinite copies of our universe, the Level 2 multiverse gives us a vast ensemble of universes, each potentially unique in its fundamental laws, born from a cosmic froth of eternal inflation. It's a truly profound idea that shifts our perspective from the universe to a universe, one among an unimaginable multitude. These bubble universes are generally considered to be causally disconnected from each other. They are like separate islands in a cosmic ocean, forever unable to interact or exchange information. This makes them incredibly difficult to test directly. However, some theoretical models propose that if two such bubbles ever collided in the very early universe, they might leave a subtle bruise or imprint in the cosmic microwave background radiation, a tantalizing, albeit speculative, avenue for future observation. As you can see, the concept of parallel universes is far richer and more varied than just the quantum branching we discussed previously. We've moved from the microscopic quantum realm to the macroscopic cosmological scale, exploring how vastness and cosmic evolution itself might give rise to other realities. We've covered the quantum multiverse of many worlds, where every possibility unfolds. We've considered the Level 1 multiverse, where infinite space ensures infinite repetitions of our own universe. And now, the Level 2 multiverse, where entirely different universes with different laws bubble into existence. Each of these interpretations profoundly redefines our place in the cosmos and challenges our understanding of what reality truly is. And this, my friends, is still just the beginning of our exploration. There are even more exotic and mind-bending theories about parallel realities out there, waiting for us to uncover them. But for today, I hope you've enjoyed this journey into the cosmological multiverses. It's a lot to digest, I know, but that's the beauty of explaining things slowly, isn't it? If you found this exploration fascinating, please consider subscribing to Dreamy Science for more cosmic adventures. And as always, I'd love to hear your thoughts in the comments below. Do these cosmological multiverses feel more or less plausible to you than the quantum many worlds? Until next time, keep looking up, keep asking questions, and keep dreaming big. Alright friends, we've journeyed through the infinite expanse of a Level 1 multiverse, where every cosmic configuration repeats itself an unfathomable number of times. We then plunged into the mind-bending concept of the Level 2 multiverse, born from eternal inflation, where entire bubble universes drift beyond our causal horizon, each potentially governed by entirely different physical laws. It's a dizzying thought, isn't it? The sheer scale of possibilities is enough to make your head spin. But hold on to your hats, because we're not done yet. We're about to delve into two more classifications that push the boundaries of our understanding even further, stretching the very definition of what a universe can be. And, in a fascinating twist, one of these levels brings us right back to a concept we explored in detail a few chapters ago. Let's talk about this Level 3 multiverse. Now, if you've been with us since the beginning of this series, this next idea might sound incredibly familiar, and for good reason, because the Level 3 multiverse, as categorized by physicist Max Tegmark, is our old friend, the many worlds interpretation of quantum mechanics. Remember our deep dive into the bizarre, counterintuitive world of quantum mechanics? We grappled with superposition, where a particle exists in all possible states at once until it's observed. We confronted the measurement problem, that perplexing moment where observation seems to force a quantum system to choose a single reality, and then we introduce the radical, elegant, and profoundly unsettling solution offered by the many worlds interpretation. There is no collapse. Instead, every time a quantum event has multiple possible outcomes, the universe itself branches, creating a new, equally real parallel universe for each outcome. So why categorize MWI as a level 3 multiverse when we already discussed it? The distinction here is crucial and lies in how these parallel universes arise and what makes them different. Think about it. Level 1 multiverse involves universes that are spatial repetitions within an infinite cosmos, all sharing the same fundamental physical laws and constants. They're just incredibly far away. Level 2 multiverse involves universes that are causally disconnected bubbles, potentially having different fundamental physical laws and constants born from the chaotic dance of eternal inflation. The level 3 multiverse, the many worlds interpretation, is different. These parallel universes are not spatially separated or causally disconnected in the same way as level 1 and or 2. Instead, they are quantum branches that emerge from every single quantum interaction. Crucially, these parallel universes, these many worlds, are all governed by the same fundamental physical laws and constants as our own. The only difference between them is the specific outcomes of quantum events. Imagine that cosmic coin flip we talked about. In a level 2 multiverse, the coin might be made of different elements in a universe with a different gravitational constant. In a level 1 multiverse, an identical coin flip is happening trillions of light years away. But in a level 3 multiverse, your coin flip creates two branches right here, right now, one where it landed heads and another where it landed tails. The laws of physics are identical in both branches, only the specific result of that quantum-influenced event has diverged. This is why, conceptually, Tegmark places MWI in its own category. It's not about grand cosmic separation or varying fundamental laws, but rather about the continuous, instantaneous branching of reality at the quantum level, where every possibility allowed by the Schrödinger equation is realized in its own universe. Your many yous in the level 3 multiverse are fundamentally the same person with the same basic physical makeup, evolving along different paths due to an endless series of quantum choices and events. It's a powerful idea because, as we discussed, it neatly solves the measurement problem without introducing any new, arbitrary rules into quantum mechanics. It simply takes the existing equations seriously, suggesting that the wave function never truly collapses, but rather describes a continually branching reality. The challenge, of course, remains the same. How do we ever observe or interact with these other branches? Decoherence, as we learned, rapidly isolates these parallel realities, making them effectively inaccessible to one another. While the level 3 multiverse brings us back to familiar territory, it's worth revisiting to appreciate its unique place in the grand tapestry of multiverse theories. It's a testament to the elegant yet profoundly strange implications of quantum mechanics itself. Now, if you thought the ideas of infinite cosmic repetitions, bubble universes with alien physics, and constantly branching realities were mind-bending, prepare yourselves, because the final level, the level 4 multiverse, takes us to a place so abstract, so fundamental that it challenges our very definition of existence. The level 4 multiverse posits something truly radical. All mathematically consistent structures exist as parallel universes. Let that sink in for a moment. All mathematically consistent structures. Not just our interface, it's yours. Not just slight variations of it, but every conceivable universe that can be described by a consistent set of mathematical equations. What does this even mean? Imagine mathematics not just as a tool we use to describe our universe, but as the underlying fabric of reality itself. In this view, our universe isn't just described by mathematical equations, it is a mathematical structure. The laws of physics, the fundamental constants, the very dimensions we inhabit, these are all components of a vast, intricate mathematical framework. If that's the case, then the level 4 multiverse suggests that any other mathematical structure that is self-consistent, that doesn't lead to logical contradictions, also corresponds to a real, existing universe. Let's try an analogy. Think of all possible computer programs. Some programs might be buggy, full of errors, and simply crash. Those are inconsistent, but for every program that is logically sound, that runs without contradiction, that produces a coherent output, each of those programs could be considered a universe in the level 4 sense. Some might be simple, like a basic calculator program. Others might be incredibly complex, simulating entire virtual worlds. In this framework, our universe, with its specific laws of gravity, electromagnetism, and quantum mechanics, is just one particular mathematical structure among an infinite ensemble of others. There could be universes where space has 10 dimensions, or 2 dimensions, universes where time flows backward, or where there are multiple time dimensions, universes where the fundamental constants are entirely different, leading to wildly different forms of matter and energy, or perhaps no matter at all, just pure energy fields, universes where logic itself operates under different axioms. This is not about universes created by a Big Bang or by quantum branching. It's about universes that exist simply by the virtue of their mathematical consistency. They don't need to be physical in the way we understand it. Their existence is purely mathematical. This concept has profound implications. 1. The ultimate anthropic principle. If every mathematically consistent universe exists, then it's no longer a mystery why our universe is so perfectly fine-tuned for life. Among the infinite possibilities, there must be mathematical structures that allow for the emergence of observers like us. We simply find ourselves in one of them because that's the only kind of universe capable of producing observers. It's not a miracle, it's a statistical inevitability within their vast mathematical ensemble. 2. Redefining reality. This level pushes us to question what real truly means. Is a mathematical structure real if it's not physically observable or interactable in the traditional sense? If our universe is a mathematical structure, does that make it any less real? Proponents argue that if physics is ultimately mathematical, then the mathematical structures are the reality. 3. No external laws. In the level of multiverse, there is no need for an external creator or a set of laws that govern the universes. Each universe is its own self-contained mathematical system, its laws inherent in its structure. There's no higher level meta-law dictating which mathematical structures get to exist, they just do. 4. The nature of physics. This perspective suggests that physics isn't about discovering external laws, but about discovering the specific mathematical structure that corresponds to our reality. It's like being an anthropologist studying a single culture, knowing that countless other cultures, mathematical structures exist, each with its own unique rules and languages. Of course, the level 4 multiverse is the most speculative and for many the most philosophically challenging of all the multiverse theories. Its untestability is even more pronounced than the others. How could we ever hope to confirm the existence of universes that operate under entirely different mathematical axioms? Our current physics, Our very language is built upon the mathematical structure of our universe. Trying to look for a level 4 universe would be like a character in a video game trying to understand the source code of a completely different game engine. Yet, despite its abstract nature, the level 4 multiverse offers a compelling and ultimate answer to the "why us" question. It suggests that reality is far grander, far more diverse, and far more fundamentally mathematical than we can possibly imagine. It invites us to consider that perhaps the most fundamental aspect of existence is not matter or energy, but pure mathematical abstraction. So where does this leave us? We've journeyed from the familiar concept of choices leading to different outcomes through the quantum realm with its branching realities, out into the cosmic expanse of infinite identical copies, into bubbles of radically different physics, and finally into the abstract landscape of all possible mathematical universes. Each level of the multiverse from level 1 to level 4 builds upon the last, stretching our minds to encompass ever greater scales of reality and possibility. It's a lot to take in, I know, and if you're feeling a little overwhelmed, or incredibly inspired, or even a bit skeptical, that's perfectly normal. These aren't just scientific theories, they are profound philosophical statements about the very nature of existence. They challenge our intuitive understanding of the universe and force us to confront questions about identity, free will, and the meaning of our own existence in a potentially infinite cosmos. We've now covered the major classifications of parallel universes, moving from the quantum to the cosmological, and finally to the purely mathematical. In our next chapter, we'll take a step back and reflect on the common threads, the biggest challenges, and the enduring allure of all these multiverse theories. We'll discuss the criticisms, the philosophical implications, and what it truly means for science to explore ideas that seem, at first glance, utterly untestable. But before we do, I'd love to hear your thoughts. Which of these multiverse levels resonates most with you? Which one feels the most plausible or the most utterly fantastical? Drop a comment below and let us know. And if you're finding this journey into the heart of reality as fascinating as we are, please hit that like button and subscribe to Dreamy Science for more explorations into the universe's greatest mysteries. Your support helps us continue these deep dives. Thank you for joining me on this incredible intellectual adventure. The universe, or perhaps the multiverse, continues to surprise and inspire us, doesn't it? All right, my curious cosmic travelers, we've journeyed through some truly mind-bending terrain, haven't we? From the quantum weirdness of Schrödinger's cat to the dizzying expanse of an infinite cosmos, and finally to the abstract beauty of a universe made purely of mathematics. We've explored level 1, 2, 3, and AVO multiverses, each one stretching our understanding of reality a little further, a little wider. Now, as we stand at the precipice of these incredible ideas, it's natural to ask, what does it all mean? How do we reconcile these distinct yet sometimes overlapping visions of reality? Are they competing theories, or do they paint a grander, more intricate picture together? Let's take a deep breath and gently piece together this cosmic puzzle. Remember, these levels aren't necessarily mutually exclusive. Our universe could be just one bubble in a level 2 multiverse, born from eternal inflation, residing within an infinite level 1 expanse, all while its fundamental quantum mechanics necessitates a level 3, many worlds branching. And perhaps, underlying it all, the very fabric of existence is a level 4 mathematical structure. Imagine that. It's like a nested doll of realities, each layer revealing an even more profound mystery. The sheer scale of this possibility is almost too vast for our minds to grasp. We're talking about not just one universe, but an infinite number of universes, each with its own variations, its own physical laws, its own unfolding destinies. And within that, an infinite number of yous living out every conceivable choice and outcome. This brings us to one of the most profound implications of our journey, the redefinition of us, our identity, our choices, our very existence. If the many worlds interpretation is correct, then every quantum event, every decision point, branches off into countless parallel lives. There's a you who chose coffee, and a you who chose tea, a you who turned left and a you who turned right. These aren't just hypothetical scenarios. In MWI, they're all equally real, equally vibrant realities. Then layer on top of that the level 1 multiverse where, given infinite space, every possible arrangement of matter must eventually repeat. This means somewhere, unimaginably far away, there isn't just a you who made a different breakfast choice, but an identical copy of you living out an identical life right down to the last quantum fluctuation, until perhaps a single choice sets you on divergent paths, and beyond that another identical copy, and another, stretching out to infinity. Your entire life, every memory, every thought, every moment is being replicated an infinite number of times across a cosmic tapestry. It's a dizzying thought, isn't it? It challenges our most fundamental sense of self. We tend to think of ourselves as singular, unique entities, moving linearly through time, but the multiverse suggests a far more fragmented, yet infinitely expanded identity. Are you the sum total of all these yous? Does your consciousness split with every branching event? Or is each you a distinct individual, forever separate, yet stemming from the same origin point? These are questions that physics alone can't fully answer. They delve into the very heart of philosophy and what it means to be conscious. And what about free will? This is another concept that gets a serious workout in the multiverse. In the classical deterministic view, our choices are a consequence of prior events, a chain reaction leading to an inevitable outcome. But in the quantum realm, especially with MWI, things get much more nuanced. If every possible outcome of a quantum event, and by extension every choice you make, is actualized in some universe, does your choice still hold the same weight? Proponents of MWI might argue that free will isn't negated, but rather recontextualized. Your choice doesn't determine the single future, but rather selects which branch of reality you experience. Or perhaps more accurately, your choice is the act of branching, creating the realities where those choices play out. You're not choosing between possibilities, but rather actualizing them all, each in its own universe. It's not that your choices don't matter, it's that all your choices matter, each giving rise to a new reality. This perspective can be both liberating and, frankly, a little overwhelming. Every decision, no matter how small, becomes a cosmic fork in the road, spawning new universes. It imbues every moment with a profound significance, knowing that every path you don't take is being taken by another version of you, somewhere, somehow. Then we consider the level 2 multiverses, the bubble universes, with potentially different physical laws and constants. This is where the concept of life itself gets stretched. Our universe, with its finely tuned constants, allows for the formation of stars, planets, and complex chemistry, leading to life as we know it. But in other bubble universes, the laws might be so radically different that matter never coalesces, or life simply cannot arise. Or perhaps life takes forms we can't even begin to imagine, existing in dimensions or states utterly alien to our comprehension. This offers a humbling perspective. Our existence, while miraculous, might be just one tiny specific outcome in an ocean of possibilities. And finally, the level 4 mathematical universe hypothesis. If reality itself is a mathematical structure, then everything we perceive, everything we experience is simply a manifestation of these abstract relationships. Our universe, our laws of physics, our consciousness, all are emergent properties of a grand, elegant equation. This is the ultimate parsimony, suggesting that the universe isn't described by mathematics, it is mathematics. It removes the need for a creation event in the traditional sense, as all mathematically consistent structures simply exist. So what are we left with? A universe, or rather a multiverse, of breathtaking complexity and profound mystery. A reality that is far more vast, varied, and perhaps stranger than any single human mind could ever fully conceive. It's a testament to the power of scientific inquiry, isn't it? To start with simple observations, to ask fundamental questions, and to follow the logic wherever it leads, even if it takes us to places that defy our everyday intuition. These multiverse theories, while still subjects of intense debate and ongoing research, represent humanity's audacious attempt to understand the very fabric of existence. They challenge us to expand our minds, to question our assumptions, and to embrace the incredible potential of what lies beyond our immediate perception. We've covered a lot of ground together, and I truly hope that this journey has sparked your curiosity and left you with a deeper appreciation for the wonders of the cosmos. Whether these multiverses are indeed real, or simply elegant theoretical constructs, they undeniably push the boundaries of our imagination and force us to confront the deepest questions about who we are and what our place is in this grand, unfolding story of existence. This exploration, like all scientific endeavours, is an ongoing conversation. The theories we've discussed are continually being refined, challenged, and explored by brilliant minds across the globe. We stand on the shoulders of giants peering into the unknown, always seeking that next piece of the puzzle. What are your thoughts on this incredible journey? How do these ideas resonate with you? Do they fill you with awe, or perhaps a touch of existential vertigo? I'd love to hear your reflections. Drop a comment below and let me know which aspect of the multiverse you found most fascinating or most challenging. And if you've enjoyed this deep dive into parallel universes, please hit that like button, share this with a fellow curious mind, and subscribe to Dreamy Science for more journeys into the heart of reality. Thank you for joining me on this incredible adventure. Keep looking up, keep asking questions, and never stop wondering about the infinite possibilities that might just be out there and in here.